Okay, friends, in the last lecture, we had discussed about the capability curve of synchronous generator. What's the active power and reactive power limits? What are the active and reactive power limits for the synchronous machine based on the stator heating limit, then rotor field winding heating limit, then the stability limit, then overexcitation and underexcitation limits. So these things were analyzed based on a regime, the capability regime of the synchronous generator in a plot where P versus Q was drawn. Now, here in this lecture, we are going to see the effect of load characteristics on voltage stability. The voltage regulating devices along with the loads will have significant effect on voltage stability. We have already seen the effect of underload tap changes on voltage stability, how underload tap changes cumulatively affect the voltage drop. We have seen that. Now, in addition to this, we have several load characteristics. It is important to note that modeling a particular load for stability analysis is very important. It's significant to model it properly or accurately so that our analysis is more realistic. Now, the voltage dependent loads effect or the behavior of this voltage dependent load, it is different compared to the constant PQ load because when using static tools in power system, suppose we are running a load flow, in the buses are assigned as either PQ bus or PV bus or slack bus. So for a PQ bus, we know that P and Q are already constant and V is free, voltage is free. So when the voltage is changed, if there is a voltage dependent load connected to that bus, then because of the change in voltage, P will also change, or both P and Q may change. Of course, for PQ bus, we have a limit for V, and for PV bus, we have a limit for Q. So the QV coupling is already taken care of by this constraint. But if P is changed because of the voltage change, then that must be accommodated accordingly. So the modeling of load is important there. Now, the system voltage is determined by the composite characteristics of load and transmission system is very important. Now, when distribution voltages remain low for a few minutes, thermostats and other load regulation devices restore and continue its sustained operation, which further drops the voltage. Say we have an air conditioner. We have several air conditioners connected in the distribution system as domestic and commercial loads. So if the voltage is low, the working of the air conditioner is such that it operates for some time until the temperature reaches the set temperature, and then it will switch off. Then again it will switch on for some time, then it will switch off according to the temperature set, according to the room temperature set by the user. So if the voltage drops, then the duration of operation of the air conditioner, this will be longer. So actually what happens is, because of the voltage drop, already there is a problem in the system, right? The system is already stressed. With this, if the duration of such heavy loads, if it is longer, then it will cumulatively affect the voltage drop, or this will compound the problem, the issue with the voltage profile. So this is another aspect. Then induction machines may stall at 85% to 90% of the rated voltage, and then they draw high reactive current. So then the voltage will reduce further. So this is another issue. So loads need to be modeled accurately, as we have already mentioned. Now, use of shunt capacitors free up spinning reactive power reserve in generators. So normally for a shunt capacitor, if it is a switching capacitor, if it's an automated switching kind of capacitor based on the sensed voltage, the capacitor switches itself. It has a regulation curve in which the maximum reactive power that can be supplied by this particular switching capacitor is fixed. So when it hits the limit, this Q supplying limit, after that it acts as a simple capacitor. It's just a simple capacitor connected to the circuit. Now the problem is the Q injected by capacitors is proportional to voltage squared. So if the voltage drops, then the Q injected will drop by square of voltage. So even though the drop in voltage is less, the Q injected may reduce by a larger value. So this actually proliferates the voltage reduction issue. So for small variations in voltage, especially if the voltage profile is already bad, then this will proliferate the issue. In contrast to this, the STATCOM and synchronous condenser, these compensating devices are possible to compensate even at very low voltages. So they have better reactive power injecting capability. Of course, STATCOM can even use a battery to compensate momentary active power fluctuations also. So this is more relevant for lower voltage profiles when compared to SVC. SVC, similar to this underload tap changer, it has a cumulative effect on the voltage instability or voltage dropping voltage profile. Now, series capacitors. Series capacitors supply reactive power based on the supplied reactive power is proportional to line current squared, and it is independent of bus voltage. So this is favorable for from stability point of view. This is favorable. The action of series capacitor is favorable. Of course, when the load increases, the current that is transferred from the sending end to receiving end increases, and more Q must be supplied because I squared X loss will increase. So more reactive power must be supplied to the system. So this automatically happens, and the proliferation of voltage drop issue is not there with the series capacitor. Now, so these are the effects of different devices, reactive power compensating devices and load characteristics on the voltage instability or voltage stability. Now, in the coming lecture, the continuation of this is to start with the QV curve, how we'll analyze the QV curve and how we will generate the QV curve. Thank you.